right, today we're going to pull back the curtain on what feels like a magic trick, but is pure science, change itself. We're going to dig into the hidden rules that control how basically everything transforms from one thing into another. This is going to be fun.
I mean, have you ever really stopped to think about it? How does a brand new car eventually get all that flaky red rust? Or how does this sticky, gooey dough puff up into a perfect loaf of bread? And come on, how does a firefly just glow? It's not magic, right? Nope. It's all chemical reactions, and they all play by the same rulebook.
Okay, so if we're going to crack this code, we have to start at the very beginning. We need to get a handle on the secret behind all this change, like what is actually going on down at the molecular level.
You know, the core idea here is actually pretty simple. You've got your starting ingredients. We call those reactants, and they get transformed into something totally new, the products. The real secret, the magic, is all about the bonds between atoms. A chemical reaction is really just a big reshuffle. Old connections break, and new ones form. That's it.
But here's the catch. Reactions don't just happen. You can't just throw flour and eggs in a bowl and hope for a cake, right? You need a recipe. You need the right conditions. And that brings us to our very first rule, figuring out what it takes to get the party started, the spark.
So this recipe, it's got three main parts. First, your reactants have to get up close and personal. They have to actually mix together. Second, just mixing them often isn't enough. They usually need a little push, some kind of energy to get going. And finally, some reactions are a bit lazy. They need a helping hand, something we call a catalyst, to speed things up.
Now that energy push, one of the most common ways to do it is just with plain old heat. Think about this. You can mix iron filings and sulfur powder together all day, and not much is going to happen. But the second you heat them up, bam! They react and form something brand new, iron sulfide. That heat is the kick they needed to break their old bonds and build new ones.
But hey, energy isn't always about heat. It can also come from light. When light is the trigger, we call it a photochemical reaction. A perfect example is when hydrogen and chlorine gas hang out together. They won't do much until you shine a light on them. Then they react to form hydrogen chloride. It's kind of the same idea behind why to get a sunburn or how old-school film photography worked. And for our third big energy source, we've got electricity. A jolt of electricity can literally force a reaction to happen when it wouldn't otherwise. And the most classic example of this is splitting water. You run a current through H2O, and you can actually break it back down into its building blocks, hydrogen gas and oxygen gas. Pretty wild, right?
All right, so we've got our spark, the reaction is underway. Now what? Well, it turns out pretty much every chemical reaction you can think of follows one of just four main patterns. Think of them like blueprints. And once you know these blueprints, you can start to predict what's going to happen.
Okay, blueprint number one. This is the simplest of all, combination. It is exactly what it sounds like. Just look at that formula. You have A plus B, and they come together to make AB. Two or more separate things join up to create one single more complex thing. It's basically the meet cute of chemistry.
And you want to know the most important combination reaction on Earth? It's this one right here. You take 2 parts hydrogen gas, 1 part oxygen gas, and you combine them to make water. That's right. 2 simple gases coming together to form the liquid that makes all life possible. That simple A plus B blueprint is why we're all here. It's that big a deal.
All right, so if the first one is about getting together, you can probably guess what's next, the breakup. Blueprint number 2 is decomposition, and it's the total opposite of combination. You start with one complex thing, AB, and it breaks down into its simpler parts, A and B.
We actually already saw this one. Remember splitting water with electricity? That was a decomposition reaction. It's also what happens when sunlight hits silver nitrate. If you look at the formula, you see that one big, complex compound on the left just shatters into 3 simpler things on the right. Solid silver, oxygen gas, and nitrogen dioxide gas. One thing becomes many.
Okay, blueprint number 3 is where things get a little more dramatic. This is the displacement reaction. Basically, a more reactive element shows up and kicks a less reactive element out of its compound and then takes its place. It is the great chemical swap.
So, how do we know who gets to do the kicking? It's not random at all. Chemistry has a rule book for this, and it's called the activity series of metals. It's just a ranked list of who's more reactive. Any metal on this list can displace or kick out any metal below it. So find zinc on there. See it? Now look for copper, a few spots down. That means zinc can totally kick copper out of a compound, but it doesn't work the other way around. Copper can't kick out zinc. The rules are the rules.
And that brings us to our final blueprint number 4, double displacement. So if the last one was one element swapping, think of this one like two couples on a dance floor and they just decide to trade partners. The two original compounds just swap their ions and form two brand new compounds. And this visual is just perfect for showing that trading partners idea. You start with two totally clear liquids, you mix them, their ions do a little dance and swap partners. But here's the really cool part. One of the new pairings creates a compound that can't dissolve in water. So it just appears out of nowhere as a solid, that cloudy stuff you see forming. We call that a precipitate, and it's a dead giveaway that you've just seen a double displacement reaction.
Okay, we've covered the spark needed to start a reaction, and we've got the 4 blueprints they follow. But there's one last super important rule. Every single reaction comes with an energy bill. It either pays out energy or it costs energy. So let's look at those two possibilities.
So there are two sides to this coin. On one side, you have exothermic reactions. In these, energy exits the system, usually as heat. The reaction basically gives off more energy than you put in. On the other side, you have endothermic reactions. Here, energy has to enter the system. It's constantly sucking in energy from its surroundings just to keep going. It's pretty simple to remember. Exo for exit, endo for enter.
And listen, this isn't just some abstract idea on a slide. You can literally feel this stuff. The picture on the left shows an exothermic reaction. It's releasing so much heat that the beaker gets hot. But the one on the right, that's an endothermic reaction, and it does the opposite. It pulls heat in from the outside world, making the test tube feel cold. How cool is that? So there it is, the spark, the 4 blueprints, and the energy bill. These are the fundamental rules that run the entire universe. It's what's happening in the fire of a star, and it's what's happening in the tiny circuits of your phone. But here's what's really mind-blowing. Trillions of these reactions are happening inside you, right this second, just to keep you alive. So I'll leave you with a question to chew on. Of all those reactions happening in your body, which one do you think is the most important?